Without data structures, you can't solve algorithms. And without algorithms, you can't pass a programming interview. Now the problem is, if you open a data structures and algorithms textbook, it is really mathy. And if you're like me and you got a C in 8th grade math, it's gonna scare you a lot. The good news is, once you understand data structures, they're not actually that complicated. So I wanted to explain the 5 most important data structures in this video in the way I understand them, which means as little technical jargon as possible, and just try to simplify it for you guys just starting out. Let's go. First off, let's talk about what a data structure is. Consider having a single data item like the price of a stock. Now that price on its own is not gonna mean much, but if we put it together with a bunch of stock prices, let's say the price is over an entire day, well then it becomes more meaningful. We call data items that we group together like this compound data. We have to store this data in some kind of a data structure, and choosing the right one is really important. No data structure is perfect, all of them are good and bad at different things. The way we measure how good a data structure is at doing a specific thing, like adding a new item, retrieving an item, sorting or searching, is called the big O notation. This is pretty much a measure of how well an operation scales. So if you have 10 items and then you add a million more, how much longer will each operation take? Okay, let's talk about the first data structure, which is the linked list. The atomic unit of the linked list is something called a node, which contains a value and a pointer. The value is something as simple as a number like 12, and that pointer will simply connect you to the next node in the chain, hence the linked part of linked list. The first node in the list is known as the head, while the last one that doesn't have a next pointer is known as the tail. Pros and cons of the linked list. It's really good at adding new nodes and deleting nodes because we can just change where the next pointer is pointing. However, it's not too good at retrieving nodes even when we know the index, or searching, because each node is only aware of the node next to it. Data structure number 2 is going to be the array. You might already be familiar with arrays because they're super common in all programming languages. The array is quite literally a continuous block of cells in the computer memory. By keeping track of its memory location, let's say the location is 1000, it can instantly compute the location of any item inside of it. For example, let's say we want to get index number 5. We just add 5 to 1000, get 1005, and then we can pull that value directly out. As a result of this, you can probably imagine arrays are really good at retrieving items. However, consider this, your array keeps growing in size and you start running into other things in memory. For this reason, adding isn't always too efficient because we might have to move our array to a new place so it fits. Luckily, this happens under the hood in high-level languages like JavaScript and Python, but in lower-level languages, you have to declare the size of your array in advance. Okay, the third data structure, and this one is super important, is known as the hash table. You might be familiar with it because it's an object in JavaScript or a dict or dictionary in Python. I think dictionary is a great word because you basically give the hash table a word or a key and it will retrieve the definition or the value for you. Under the hood, it actually works a lot like an array. The key actually gets run through a function called the hashing function, and that will spit out a memory location for you. The way it's different is these memory locations don't have to be next to each other, they can be anywhere. So you don't have the same problem with the increasing size. However, there is a different problem. Depending on the hashing algorithm you use, 2 keys could hash to the same memory location. This is what's known as a collision, and there are different ways to resolve this, but again, it's all happening under the hood. Needless to say, the hash table is really good at both retrieving and adding, but the collisions can be a problem. Okay, fourth data structure, this is a double, is the stack and the queue. I'm grouping them together because they're pretty similar and they're both kind of built on top of arrays with a few additional features. The stack is a last in, first out data structure. Think of a stack of cafeteria trays. The last one you put on the top is the first one you have to take off. When we add an item to the top, it's called pushing, and then we pop off the top. Every language keeps track of the functions that have been called with something called the call stack. Stacks are also super important for an algorithm called depth first search, which you're gonna run into a lot. The queue, on the other hand, is first in, first out, just like any queue or line. Let's say a line to board a plane at the airport. Adding an item to the end is called in-queuing, and removing it from the front is dequeuing. Queues are used for a really important algorithm called breadth first search. Overall, stacks and queues are really efficient but have limited use cases compared to other data structures. Finally, we're going to talk about graphs and trees. This one is so big that there's an entire field of computer science called graph theory. What a graph is basically kind of similar to a linked list where you have nodes that are pointing to other nodes, except in this case, the pointers are called edges. Edges can also have weights or numbers assigned to them. Imagine two cities, New York and Boston. The road between them is the edge, and the length of the road could be the weight of that edge. Complicated relationships like social media networks are also stored as graphs. There's a special kind of a hierarchical graph called a tree in which the data expands out in one direction. We can use these to represent a lot of things too, like a family tree or even an HTML tree with nested elements. There's an even more specific tree called a binary search tree. This tree has really specific rules, but these rules allow us to do things like searching really efficiently. The rules are as follows. Each node can only have maximum 2 children, left and right. The left has to be less than the node, and the right has to be more. With these rules in place, we can traverse through our tree and always kind of know where an element is. So if I had a 5 at the top and I was looking for 7, I would know it's either to the right or not in my tree at all. Unfortunately, BST is not the perfect data structure either. If you add elements in a weird order, it can get very unbalanced or one-sided, and you lose a lot of the advantages you get with your search optimization. There are self-balancing trees, but that's getting into more advanced data structures, so we'll leave those out of here. All right, guys, these 5 data structures will give you a really great foundation to start solving algorithms. This video is not sponsored, but I would recommend checking out Code Wars first, followed by LeetCode when you get a little bit better. LeetCode has programming interview questions from actual tech companies, so it's really good to eventually get there. Anyway, guys, I hope you liked this video, and if you could leave it a like, it's free for you, so that would really help me out. And if you want to see more short, no BS tutorials, then please subscribe. All right, I will catch you guys soon.